Okay, in today's video we're going to look at partial differential equations, or PDEs, with finite differences. And the main reason that we'll use this technique is to be able to easily handle partial differential equations in which there is one time variable and two spatial variables or more. Okay, so we'll start this by looking at some physics. But it will be pretty straightforward, and then the solutions to the PDEs will be a pretty straightforward or easy method that we introduce as well. So this may not seem as difficult as even the analytic methods that we did in the previous section, even though they're more spatial dimensions in this case. So we'll start by this definition. Let f be a function of x, y, and z. Then the gradient vector, or grad f, is the vector consisting of the vector where each of the coefficients of I, j, k are the differential operators. So d on dx, d on dy, d on dz. So this here is a vector operating on f, and so we have the vector partial derivative of f with respect to x in the I direction, partial derivative of f with respect to y in the j direction, and partial derivative of f with respect to z in the k direction. So this upside down triangle here is called the del operator. Alright, let's consider a physics definition now. Heat flux is the quantity of energy that flows through a surface per unit area per unit time. Now, Fourier's law of conduction says that if phi is the heat flux passing through an area A, then that heat flux is proportional to the gradient vector of T. So, in other words, minus k grad of T, where k is the conductivity constant of the material and A is the area perpendicular to grad T. So grad T, remember, is a vector. So if I had a surface that heat was passing through, then grad T would be perpendicular to that. And heat passing through. Okay, if Q is the energy passing through the area A in time, then the rate at which the energy changes with respect to time, or dq on dt, is phi times A. The Laplacian operator is the dot product of this del operator, so del dot del. And now when you take the dot product of two of these vectors here, remember you have then the I coefficient gets multiplied with the I coefficient, so we have d2 on dx squared for the first part of it, and we add these results together because it's a dot product. So we have the operator that consists of the sum of the second order partial derivatives in space. So Laplacian of f is the sum of the second order partial derivatives. Now if we have only two spatial dimensions, say x and y, to worry about, then the Laplacian operator applied to f is the sum of the second order partial derivatives in x and y. So just what we have here at the bottom. Okay, so that brings us to the heat equation in general, right? So previously in the previous chapter we saw the heat equation in one spatial dimension and one time dimension. There is only one time dimension. And we solved that analytically. So now we're going to present a numerical approach to solving that, but it's very easy to do and very easy to set up. But we won't actually do any solving of the linear systems that result. Okay, so let's let T be the temperature of a point XYZ on an object. Now this could be a barbecue plate or a block of metal that's being heated. So the temperature of the point on an object in time, so that t of x, y, z, and lowercase t, where lowercase t is time, it's a function of those letters. So the heat equation says that the rate of change of the temperature with respect to time is proportional to Laplacian of f. So in other words, equal to k times nabla squared of t. Just as we see here, where k is a constant. Now that constant depends on the material. For example, my mother told me that I should be cooking with an iron pan because it has a very good retention of heat, and so that has a different number k. All right, definition 5. Let's let T be the temperature of a point x, y, z on an object in time, so that T of x, y, z, and t is a function of those letters. We say that an object is in thermal equilibrium if for all points inside the object, the temperature at the point is not changing with respect to time. And so that is the rate at which the temperature changes with respect to time is equal to 0. So not changing with respect to time at any of those points x, y, z within it. Now how could that happen? Well, if it were insulated perfectly along the edges of, say, the block of metal or other object, then that rate of change would be 0, right? Okay, so it follows from the definitions that if a body is in thermal equilibrium, then the temperature satisfies Laplace's equation. Because what we're doing is we're taking this heat equation here, and if the left-hand side is equal to 0, we can divide throughout by k, and we just have nabla squared of t is equal to 0, which is Laplace's equation. If the object is a flat two-dimensional surface, so we don't have to worry about any height, we just have an x and a y, then Laplace's equation looks like this. So it's the sum of the two second-order partial derivatives equals 0. Okay, now let's look at a few analytic solutions to this equation, Laplace's equation. Harmonic functions. A function f is harmonic if f is twice continuously differentiable on an open subset of Rn, meaning that the derivatives exist and they're continuous, and f satisfies Laplace's equation. Okay, so if those two things are satisfied, then we can call that function harmonic. Okay, a linear combination of harmonic functions is a harmonic function. So what that means is if I have one harmonic function, say f1, and another harmonic function, say f2, and I multiply f1 times some constant and f2 times some constant, and I add those two together, then the result will be another harmonic function. So you can imagine then that there are infinitely many harmonic functions. So infinitely many solutions to Laplace's equation. Alright, so this here is a little bit of a demonstration of this fact. Let the set of the f subscript I be a set of harmonic functions. Then for each of those functions f subscript I, nabla squared of f subscript I is 0. So that is, they satisfy Laplace's equation. Now let's let g be equal to a sum of constants mi times fi. Add those two together. In other words, just form some linear combination and call it g. And let's take nabla squared of g. So that would be nabla squared of the sum of the mi times fi. Okay, now we can apply that differential operator on the inside of the sum. But since the mi are constants, we can move that out in front of nabla squared. And so we see that we must have the sum of the mi times nabla squared of the fi is 0. Because each of the nabla squared of the fi is 0, so the sum of those has to be 0. So therefore we see that nabla squared of our new function g has to be 0 and therefore must satisfy Laplace's equation also. Let's have a look at an example of two harmonic functions. Okay, so in example 12.1, let f be equal to x squared minus y squared and g be equal to the natural log of the sum of the squares, x squared plus y squared. Both of f and g are harmonic functions. So let's have a look. So taking the first partial derivative, and actually I think I want to open up a window. And I'll just do some of these calculations in a little bit more detail. Alright, so if I have f equal to x squared minus y squared, and I take a partial derivative, hang on, okay, so I'll find the right symbol for this. Okay, so the partial derivative with respect to x of f is, now we're treating all other constants other than f, all other variables other than f as if they are constants. And so what this is, when we apply that partial differential operator to these two, we have the partial derivative of x squared with respect to x, and then subtract the partial derivative of y squared with respect to x, but this partial derivative here is 0 because we're treating y as a constant. Okay, however, this is the same x as we have down here, so this is the derivative of x squared with respect to x, and so we have 2x. So we have 2x for the partial derivative of f with respect to x. Now, if we do that again, we differentiate this again. So I'm applying d on dx twice. So that means I'm applying d on dx to 2x. And so we get 2 for that. Okay, so that's the second derivative partially of our function f with respect to x. And we get 2 for that. Now similarly, for the partial derivative of f with respect to y, I'll just change these letters here. So for this, for the first partial derivative of this function with respect to y, we have minus 2y for that. Okay, if we differentiate that again with respect to y, then we have minus 2. Alright, now adding those two together is 2 minus 2, which is 0. Okay, so it satisfies Laplace's equation, as in the difference of these two squares does. So similarly, the natural log of the sum of the squares will as well. And so I'll just show you here. I'll just say g is equal to the natural log. Here, I'll just type in log. X squared plus y squared. Okay, I'm going to use the computer to calculate this one, just to be quick about it. So the first partial derivative is 2x over x squared plus y squared. And then if we were to differentiate that again with respect to x, then we have this, but we might want to factorize that. So I'll just say factor. Okay, so this is what we have when we factorize that. So this is this one here. I'll just put this in as a comment. But it's the partial derivative of g with respect to x squared. Okay, now if we do the same thing with respect to y, you see these look very similar, right? Now the difference in these is that this first part of the numerator is the negative of the other one. So if I were to add these together, I would get 0 because this is the negative of this one right here. So we add those together and we get 0. Okay, so both of those functions f and g satisfy Laplace's equation. Now by the theorem that we saw on the previous page, any linear combination of those will also satisfy Laplace's equation, and incidentally a constant does too. So for example, 3f plus 5g plus 7 satisfies Laplace's equation and is therefore a harmonic function. So we can produce an ever-increasing number of solutions to Laplace's equation. Alright, so let's look at another example here. Imagine we have a thin, flat 1 meter by 1 meter plate. The faces are insulated so that no heat flows across the faces, only across the edges. The plate's in thermal equilibrium. If we know the temperature along the edges, can we work out the temperature on the inside? Alright, so suppose we're given the function t of xy is 100x times 1 minus y squared. Now this satisfies the boundary conditions, but not Laplace's equation. So if you take the partial derivative of this with respect to x, you have 100 times 1 minus y squared, and then differentiate again and you get 0. But then you do that with respect to y, so the partial derivative of t with respect to y is minus 200x times y. Then you differentiate again with respect to y and you get minus 200x. So that nablus squared of t is minus 200x, which is non-zero. Alright, so it's easy to find a solution that satisfies, say, the boundary conditions but not Laplace's equation, and one that satisfies Laplace's equation but not the boundary conditions. Okay, now let's look at this function, x squared minus y squared. So we know that this satisfies Laplace's equation because we just did this in example 12.1, but it doesn't satisfy the boundary conditions. And I probably should have specified the boundary conditions in here. I think it probably was in a picture there that was not carried through when I compiled this. Okay, so this doesn't satisfy the boundary conditions here. And so it's not an easy problem to analytically solve for a function that both satisfies Laplace's equation and satisfies the boundary conditions, that is the temperature along the boundaries of your metal plate. So this here is my metal plate. It's insulated on this face, it's insulated on the back face, and we know the particular temperatures along the edges here, right? So these are what I would call the boundary conditions here, where we know the temperatures here and here. We have a solution that satisfies Laplace's equation, but that solution, that analytic solution, doesn't satisfy what we know the temperature along the sides to be, right? So that's why this is a difficult problem analytically. So what we do instead is we use numerical methods to solve this problem. Okay, so basically only numerical methods can compute a function to satisfy both Laplace's equation and the boundary conditions. Alright, so let's have a look at what we do to solve this problem. So finite differences are a tool that we use to satisfy both Laplace's equation and the boundary conditions. Now what are they? What we do is we simply approximate each of our partial derivatives using what looks like the definition you would have first learned for the first derivative. Alright, so the definition that you would have first learned for the first derivative is the definition of a derivative by first principles, which would say go step ahead one and take the slope of a chord and then let that the horizontal distance decrease until your chord becomes the tangent line, right? Hopefully you can remember that. However, we can form a decent approximation of the first derivative by taking the slope of that chord. So f of x subscript I plus 1 minus f of x subscript I minus 1 all over 2h, where h is the difference between those x points, xi plus 1 and xi. So this one here is called the central difference approximation of the first derivative. So we step one h value ahead and one h value behind on our function. We form a chord. We take the slope of that chord, and we suppose that that's approximately equal to the slope of the tangent of the curve. Now you can do something similar with the second derivative, and a second derivative approximation is 1 on h squared f of x subscript I plus 1 minus 2 f of x subscript I plus f subscript I minus 1. Now we can use these two derivative approximations with partial derivatives as well. There's not much difference. So with a partial derivative, remember the partial derivative of f with respect to x measures the slope of your surface in the direction of the x-axis, so with a slice that's parallel to the x-axis. And so an approximation of the partial derivative of f with respect to x using this equation 40 here, it would look like 1 on 2h times f of xi plus 1 comma yi minus f of xi minus 1 comma yi. So we're keeping the y value the same in each of these, right? But we're moving ahead in the x value and behind in the x value. So we can form a chord on the vertical slice that's parallel to the x-axis there. Okay, now something very similar for the derivative approximation, or the partial derivative approximation of f with respect to y. We step ahead in the y value and behind in the y value, take a difference, divide by 2h. Now similarly, we can just use this equation 41 for the second partial derivatives as well. Alright, so we fix the y values here, and the approximation of the second derivative of f with respect to x. And in the second derivative of f with respect to y, we fix the x values and we move ahead and behind in the y values. So these two, equation 44 and 45, are approximations of the second order partial derivatives of f with respect to x and with respect to y respectively. So therefore we can use these to approximate Laplace's equation just by adding those two together. So the approximation of nabla squared is the sum of these two in equation 44 and 45, right? But we can factor out the 1 on h squared, and since we have 0 on the right hand side due to Laplace's equation, we can multiply throughout by h squared, so that that 1 on h squared cancels. Alright, and so what we get is minus the sum of each of these, so minus f x subscript I plus 1 comma yi, and then moving back in the x and fixing the yi, then the yi changes while the x is fixed. But then this one, 4 f of xi yi, there are 4 of those because we have minus 2 here and minus 2 there. You see, in this equation 46, I've also multiplied through by minus 1. Now, you don't have to do that. So we could leave the coefficient 4 as minus 4 there, rather than to multiply throughout by minus 1. But what we get from this is a template that we apply to grid points. Now, have a look at the right-hand side of my page here, where I've got little dots on this square. So what we're doing is we're moving this template over each one of these points one by one and writing down an equation. that gives us the approximation of Laplace's equation over each of these points. So this is our template that we get from this. So the sum of each of these multiplied by the variable values at those points, this adds up to 0. Okay, so it'll make more sense when we see this example here on the next page. So let T1, T2, dot, 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 up to T16 be the temperatures at the grid points in this picture here, from left to right and top to bottom respectively. Now you can do that with like matrix type subscripts as well, which is probably more appropriate than what I've done here. Alright, so in this picture we've got a metal plate in thermal equilibrium, so it satisfies Laplace's equation. Now let's suppose that this width is 1 meter, the height is 1 meter, so the step size here, the h value will be, let's see, 1, 2, 3, 4, 5. There are 5 little partitions there, so that would be 1 divided by 5 is 0.2, so h there would be 0.2. Okay, so we need the temperature on the boundary in line with the grid points. Now so these equations along the boundary give us the temperature along these boundaries. So if you focus on the top, it says Tx, 1 is equal to 0, so that means x changes along that boundary line, but y is equal to 1. So it tells you that the temperature along this top is entirely 0. Okay, now this one over here says the temperature on the left-hand side is also entirely 0, but the temperature along the right-hand side is changing as y changes. So as y goes up, you have ever-increasing values of y to sub in, so the temperature goes up along the right-hand side of this little square. And incidentally, it's this picture that I'm talking about in the in example 12.2. because it's not easy to find an analytic function that satisfies Laplace's equation and the boundary conditions where these are the boundary conditions here. So we go for a numerical approach. Alright, so what we do is then we sub in, so for the bottom here, Tx, 0 equals 100x, we're subbing in the x values at the points. So the first x value is 0.2, then we have x is 0.4 and 0.6 and 0.8 and 1. Alright, so along the bottom, x is 0.2 and y is 0, so we have 20. And all we're doing here is multiplying 100 times 0.2 and we get 20. Okay, t of 0.4, 0, so we multiply 100 times 0.4 and we get 40. And so on and so on. Okay, so up to 80, that includes the bottom. Now the right-hand face, we fix x is 1 and we put in y is 0.2 to get the point right here where my mouse is. Okay, so that should have temperature 96. Then up 1 we get temperature 84. We're just subbing into this function right here. And then 64 and then 36. Alright? So we have all of these boundary conditions, and on the left-hand side we have 0, on the top we have 0. So we apply Laplace's equation, the template, this template at the bottom left here, we apply it to the top left grid point there. Okay, now it says minus the left one, which is 0, minus the top one, which is 0, and then minus this right one, but that's a variable value, t2. So minus t2, which we see right here, and then below that, which is this, minus t5, and then plus 4t1, which is over the center of the template. Alright, so I'm going to look at the next page. Now, okay, so what I think I'll do here is take a screenshot of this page, and then I'll open it in Paint, and I'll draw on it. Alright, so I'll get a pencil in red, make it big. So what I'm doing here with my template is I'm taking it around here, right? And here I have variable value t subscript 1 over here, t subscript 2, and this down here is t subscript 5. It's a bit hard to draw here in Paint. And then we know this value is 0 because we checked the boundary. This is 0 here. So that's how we formulate this equation down here. Okay, using the template, which looked like -1, -1, 4 in the middle, -1, -1. So I multiply these coefficients by the variable values there displayed in the template to form this equation, right? And the right-hand side is 0 because of Laplace's equation. So we have approximated Laplace's equation at the point t1. Okay, now we do this 16 times for the 16 points that we have there, the 16 grid points. So next we move it over to the right, apply the template there, right? Then we move it over again, and we move it over again. All right, and then we go down the row and do it again, again, again. So therefore we would get 16 equations. All right, I'll minimize this now and we'll go back to the PDF. So the second one, when I move the template over T2, I have minus T1, I have minus T3, I have minus T6, and I have 0 above. And then I have 4 T2, okay, equals 0. So the sum of those equals 0. So we're going to get 16 linear equations from this. All right, let's have a look at the next page. So these are all the equations that we form from moving that template over each of the grid points. Okay, now collected all together, these here are what is it, 7 or 8 of them, and then here are the further 8 of those. So that this together with this is the full system of 16 equations and 16 unknowns. Now you can write that as a matrix equation, which is what I have displayed next. Okay, and so you move the template over each of those grid points, you formulate your equations, then you want to write your equations as a matrix, and then of course you want to solve it, right? But I will leave the solving of the matrix equation out of this course because that would be a numerical approach. All right, but you can imagine it's not too difficult. Now I'll just give you an example. So if we were to use the software Python, which is free software incidentally, and many people are fond of it, so I would enter that matrix in the following way. So A equals array, round brackets, 2 square brackets, then I'd enter the first row, then the second row, and so on, right? And it continues on. Okay, and then I would enter the vector that I have as the coefficients on the right-hand side. Now what these numbers are, incidentally, is the right-hand side of these equations here, but we have those there because what we've done is we've taken the temperatures. For example, have a look at this one where it says minus 96 and minus 80 there. So these are temperatures along the boundary that we got when we applied the template over the 16th point, or the bottom right. Let's have a look at that. Over this one right here, we have non-zero numbers where my mouse is there and there as well, because we have non-zero boundary conditions along the bottom and the right-hand sides. So we get numbers there, right? And so when you take those numbers and you put them over on the right-hand side of the equation, you now have non-zero numbers on the right-hand side of the equation. All right? So, so from there, we write the 16 by 16 matrix multiplied by the vector consisting of variable values t1, t2 up to t16, and that equals the vector that is the right hand side of each of these equations. Okay, so you want to enter this in some software, right? So which is like this: we enter the array B, which is the right hand side, and then we just say solve A comma B, right, which will give us a solution to that linear system. Now of course you could do it by hand, but it would take forever. All right, So in the tutorial, we're just going to basically set up problems, apply the grid template, or sorry, apply the template over each of the grid points, write down the equation. It'll probably be a small toy example, and then we understand that we are able to find the numerical values by using software. All right, so then this Python program would give us the solutions for T1 through T16, and then if you want to, you can display those like I've done here at the bottom, right? So you can see I've got 0 along the boundary, as we said earlier. The bottom, we got 20, 40, 60, 80, 100 as given by the boundary conditions, and the same on this right hand side. But what we've done is we have now solved using this numerical approach for the interior temperature values, right? And you can see it does look like it matches up with the boundary conditions. All right, so that's the technique, and it's a very simple technique. Hope you think so too. I know you guys have been making fun of me for using the word simple far too often than you think is appropriate, but I think this is fairly simple. Anyway, all right, so is this physically reasonable? All right, so now we're going back to have a look at a little bit of physics and say, is this technique that uses Laplace's equation, is that physically reasonable? Does it make sense with physics? So now take our metal slab and place cells of width h around each of the grid points, but center our template above a particular point, say xi, yi. Now we're going to consider the heat flow on the top face of the center cell flowing into the cell above it. Okay, so from here to here. We will, that's a typo there, we will denote this heat flow as h subscript n for north, which is equal to dq on dt, according to theorem 2. So the rate at which the energy is changing with respect to time through the north face of the cell. All right, so we can compute the heat flow as minus the conductivity constant, so minus k, times the width of the cell, times the thickness of the metal, times the partial derivative of the temperature with respect to y at that particular spot where we're doing this. Now, you'll see this looks a little odd here because we have y subscript j plus a half h. But if you have a look at it, we're moving up 1/2 of that cell width up to the north face there to do this. So that's why we have plus a half h. So ignoring the vector part of this, this is h subscript n is minus k h w for the width of the cell times this partial derivative. So we can do the same for the south face, the east face, the west face, centered at the point xi, yj. Right, so we can write all of these similarly and then use our approximation of that first partial derivative there. But incidentally, this is just this, what is it, Fourier's, back here at the beginning, Fourier's law of conduction. So yeah, we're using this. All right, where were we? Okay, so we do the same for each of the other faces and we approximate those derivatives. So we have minus kw times the difference of those temperatures at each of those points. Heat flows across the faces of each cell, but since each cell is in thermal equilibrium, the total heat flow into the cell is equal to the total heat flow out of the cell, so that the rate at which the energy enters the cell and leaves the cell is 0. So that means the sum of those h's is equal to 0. Okay, so we sub each of these in, and we have minus kw times this difference, minus kw times this difference. The sum of all those is 0. So if we simplify that, we can divide away by the kw, and we get minus t xi yj plus 1 and so on. We get exactly like what we get from Laplace's equation. So it seems to be physically reasonable. All right, so in our next section here, and I'll only briefly cover this, what if we had an insulation on one side of the face? So that would be the dark gray here that you see. So what we're going to look at is called Neumann boundary conditions. So where we have a different kind of boundary condition, not just given the temperature along each of the sides, but we have a rate of change of temperature leaving one of the sides or more of the sides. Suppose the boundary x equals 1, so that's the right hand side of this, is insulated so that no heat may flow across this boundary. The temperature gradient across this edge is 0, so we're still assuming that each of the other faces, front and back, are insulated. But here, so right hand side is insulated so that the temperature gradient is 0 along there. So if we replace the boundary condition t1, y equals 101 minus y squared with a partial derivative boundary condition, so that would say the partial derivative of temperature with respect to x is equal to 0 along this right hand face. And suppose we have it given in that way. Okay, so that's what we're looking at now. Definition: for any point xy on the edge, the outward normal vector v x, y and the derivative in the direction v x, y is called the normal derivative and denoted t subscript v, where v, remember, is a vector of xy, and it's given by this directional derivative formula. So t subscript v of xy is the gradient vector of t dot the normal, the unit vector v. So we're just taking the vector v and dividing by its norm there, so it's a unit vector having unit length. Okay, simplifying this, we have a dot product of grad t and v divided by the norm. All right, so in our problem, I hat is the normal vector to the east face. So it's a very simple vector v in our case. And that's a unit vector, so we don't have to divide by the norm, which would be 1. So t subscript v 1, y is nabla t 1, y dot I. Okay, and when we take that dot product, it's just the partial derivative of t with respect to x. So just this one right here. So that's equal to 0. Okay, so that's saying basically heat's not going through that right-hand face. All right, so we would write that boundary condition like this. T subscript v 1, y is the partial derivative of t with respect to x at 1, y, which is 0. So what we do here is we create some fictitious points outside the plate, and we approximate this boundary condition, this Neumann boundary condition, using an approximation of the first partial derivative of t with respect to x. All right, so we create fictitious points and we apply this equation right here along this boundary. In other words, we've approximated this first derivative here, which we know to be equal to 0 because of the insulation. So here's the approximation of that first partial derivative. But when you multiply throughout by 2h, you see that this difference equals 0, and so you can move the t 1 minus h, yj over to the right-hand side. And so it says that t of 1 plus h, yj is approximately equal to t of 1 minus h, yj. So what this is saying in this physical picture here is the approximation of the temperature at this fictitious point outside the plate is approximately equal to the temperature inside the plate over here, right? Because we have 1 minus h, which would be here, and then 1 plus h, which would be out here outside the plate, the fictitious point. So we may apply our template that we got earlier from Laplace's equation. We may apply it along the boundary, but whenever we have to take in a point that's outside the plate here, one of the fictitious points, we replace that variable value by this point inside the plate. All right, so then along that right-hand face, replacing the fictitious point with the point inside, we have minus 2t x subscript I minus 1 comma y subscript j. We have two of those, right? And then the rest of the template as before. So I would encourage you to set up a problem like this, or just take this one right here and apply your grid to that and use this approximation here, right, which is the Neumann boundary condition, and verify that you actually get this equation. All right, so now let's do another simple problem here with a triangular metal plate. All right, so a thin triangular metal plate is insulated on both faces. So it's front and back. So no heat flows through those, only heat flows across the edges. Okay, in appropriate 2D coordinates, the plate occupies the area where x is between 0 and 1, and y is between 0 and x, or between the line y equals x is what this would say. It's what you see there in the diagram, and basically under that. Okay, so the plate's in thermal equilibrium, so it satisfies Laplace's equation. We've got the boundary conditions given as t of x comma 0, so that's along the bottom, that's equal to 0. The temperature along the diagonal face is Tx comma x is equal to 100x, because remember y equals x along that side, so that's why we have x comma x. And then we've got this Neumann boundary condition which says t subscript v 1 comma y is minus 3 brackets t of 1 comma y minus 100. And here we're going to use h as 1/3 of a meter. Alright, so next we're going to place on our grid points. Right, so we need fictitious points on the right hand face because we've got a Neumann boundary condition there. Alright, and so we're going to label these T1, T2, T3, T4, and T5, including our fictitious points. So we apply the template to T1 first, right? But you can see along those boundaries where we had equations that we could just sub in the x and the y values into and find the temperatures. I've labeled those 0, 0. So 0 down the bottom, and then we've got 33.3, 66.67, and 100. All right, but that comes from the equation Tx comma x is a 100x. So I'm just supplying in the x values and obtaining those temperatures along there. Okay, so I apply the template over T1 first. So for T1, and then minus 33.3, minus 66.67, and then minus T2, and then minus 0, so that should add up to 0. That gives us the first equation there. Now we move the template over to T2, but you see it now includes the fictitious points. So over T2, we have 4T2 minus T1, minus 0 for down the bottom, minus T3, the fictitious point, and minus T4. So that adds up to 0 according to Laplace's equation. Then we move the template over T4, We take in minus 66.67, so that's to the left. We take in the point above, minus 100. We take in the point below, minus T2. We take in the fictitious point, minus T5. And then, of course, I probably said earlier, but we've got 4T4. Okay, so that's all of the three equations that we need for moving the template around over those grid points. Simplifying that, we can move the actual constant numbers over to the right-hand side and obtain this equation here. Okay, so now let's deal with the Neumann boundary condition. So we had t subscript v 1 comma y is minus 3t 1 comma y minus 100. Now we want to replace the partial derivative, which is our t 1 comma y. We want to replace that with the partial derivative of t with respect to x, because the normal face, right? So the direction here is perpendicular to the face, so that's just the I vector. So it's very simple. So we just have a partial derivative of x with respect, of t with respect to x there. And so we apply the derivative approximation on that with h equal to a third. So then we have t3, this one, minus t1 over 2h, but that's 2 times 1/3. Okay, so that's equal to our boundary condition, right? So this here on the left, that's t subscript v, because v is just the vector I. Alright, so this gives us a little equation here, and we can rearrange this equation. So let's see, we've got 2/3 on the denominator of the left. So we want to multiply both sides by 2/3 to simplify that. Okay, and so what we get is t subscript 3 is equal to t1 minus 2t2 plus 200. Now similarly, applying this Neumann boundary condition here over t4, we have the approximation of the partial derivative of t with respect to x at the point 1 comma 2/3 is approximately t5, so going forward and then going back, subtracting minus 66.67 and dividing by 2h. Right? And so that is given by minus 3 bracket t4 minus 100. Okay, so that also gives us an equation, or a way to eliminate t5. So t5 equals minus 2t4 plus 266.67. So then we go back to the three equations that we got here after simplifying, and we replace t3 and t5, because we now have expressions for t3 and t5 that involve the other variables t1, t2, and t4. Okay, so we sub those values in to t3 and t5, and we get this at the top of the page on the right. Okay, and so now we only have three equations and three unknowns, and so we can simplify that, and we now have these three equations in t1, t2, and t4 that give us a simple matrix equation. Now you'll notice that this affected the pattern down the diagonals and about the diagonals, whereas before we had a very nice pattern in this matrix. You see, we had a very predictable pattern along the diagonal. This incidentally is what we call a sparse diagonally dominant matrix, which lends itself to special nice numerical techniques for solving such equations that are efficient. Okay, but back to this. So we had a pattern here that is slightly different than the kinds we got before. Okay, so not very surprising, because now we had a Neumann boundary condition on the right-hand side of that. Alright, so solving that one gives us t1, t2, and t4, 40, 60, and 82.29. Alright, so now that's only approximate because we've got quite a wide gap in the grid points, right? So if you wanted more accuracy to this, you would just use your step size being much smaller. You would have a whole lot more equations to have to solve, but if you have a computer, that's generally not a problem, together with good numerical techniques. All right, so this that I presented is a method for solving the heat equation using approximations of derivatives in a way in which it would ordinarily be difficult to give you analytic solutions because of the problem of finding a function that satisfies both Laplace's equation and the boundary conditions, right? However, this numerical approach is pretty straightforward. All you have to do is write down a template, move it over the grid points, write down some equations, simplify those equations, and solve. Okay, now I'm not going to go and talk about variations of this, because what comes next in this chapter are discussions of a variety of different shapes that you could have and other conditions. Okay, so I'm not going to cover that. I will say you can also use the method of finite differences on the wave equation, but it's notoriously bad because errors in the approximation really compound in the wave equation and you get what we call scattering, right? So there are certain conditions on your system for which the wave equation would be effective in solving. I mean, for which the wave equation would be suitably solved by finite differences, right? So it works well for the heat equation, but not quite as well for the wave equation. All right? Now, you could go and pick up a book and carry on your studies, you know, after you're done and after you're a teacher and so on, or an engineer or a physicist. But that's all for the theory that I'm going to present to you for now. So thanks so much. You made it through the entire course. We'll come back and do some revision of various things and some exam prep. Bye for now.